Okay, welcome to lecture. We're going to start kind of new chapter 5, and then into 6. Again, the handouts should be up there online if you need it. And again, a reminder that what we're starting today is not going to be on the exam, which again is coming up on Monday, I believe. So this will be for exam 3, I think. We'll get started in just a second. Okay, so we finished up talking about nomenclature last time, and again, that is, I think, the cutoff point for exam 2, which is on Monday. And now we're going to kind of switch gears a little bit. We're going to start talking about balancing chemical equations in general. We'll also get into different types of chemical reactions, ways to classify chemical reactions. In this chapter, or chapters, I guess. I think it kind of goes into a couple of different chapters, part of 5, part of 6, and even in reality, I think even maybe part of 10, like just a section of 10 maybe, or something like that, or 12. All right, so let's start. We're going to start with actual chemical reactions and equations. So obviously, any process in which one or more substances are changed into new substances, that's your basic definition of a chemical change. And most chemical changes involve a chemical reaction occurring. And basically what that means is whatever you start with and whatever you end up with are two fundamentally different things. So that's usually a chemical change that's occurred that usually involves a chemical reaction changing. The key to that is you can't do anything sort of physical to it, like boiling, melting, freezing, to get back your original substances. So the only way you can kind of get back to the original substances is through perhaps a chemical reaction going the other way, but there's some type of chemical change. Remember that we do have conservation of everybody in terms of elements in a chemical reaction. The only thing that happens is everybody on the reactant side basically breaks apart and comes back together on the product side. So we talked a little bit about that when we were doing those bond energy type questions, where we figured out how much energy required to break all the bonds and how much energy to put them back together on the other side. And that's ultimately what happens in a chemical reaction, is sort of that process. And because that process really only involves electrons, that's why we really do have conservation of elements. We don't change any elements or anything like that. It's just those electrons. Because as we know, elements are basically determined by the number of protons, which are in the nucleus. And in a normal chemical reaction, those guys are not involved, which means that's why, again, we do have that kind of conservation of elements. And as you'll learn, if you do take the next class there, 200B, I guess they call it here, you'll learn about nuclear reactions where that's not the case. In nuclear reactions, they actually do play with the protons and neutrons, and thus we don't really have conservation of elements. But in a chemical reaction, like we talked about in this class, and most times we talk about, you do have that conservation because it's really just the electrons involved in that process. So there's a few different ways that we can represent a chemical reaction. We can see pictures there, we could do that, but most of the time we do use an equation like what we have over here on the bottom. And in an equation on the left-hand side of the arrow, those are our reactants, which is our starting material. And on the right-hand side of the arrow, those are our products, which is what is formed as a result of a chemical reaction. So it's always reactants to products. Some other things that we commonly will sort of see in equations next to formulas is we'll oftentimes see the state of everybody. So we'll see S, L, G, and AQ. S is obviously something in the solid state. L is something in the liquid state. G is something in the gas state. AQ is the aqueous, and basically what that means is a water environment. And that is essentially what is usually used for a solution. Now, sometimes people have a question, kind of like, what's the difference between AQ and L? So the difference is sort of this idea. For example, if you just had water by itself, nothing else there, that's considered a pure liquid. There's nothing else sort of mixed with it. But if you take that water, which is a pure liquid, and then you add to it something like sodium chloride, which is a solid, and you put those together, what's going to happen is the sodium chloride is going to dissolve in the water and make an NaCl solution, which is aqueous. So aqueous usually in a lot of cases is what basically makes it a solution. And usually that is the difference is you're actually taking something with, in this case, like the sodium chloride, which is known as a solute, and dissolving it in something like water, which is a solvent. So that's really the difference, between L and AQ. L is really just something pure by itself that's in the liquid state, and aqueous is usually made by dissolving something in it. Other things that we commonly will see a lot of times written on top of the arrow here. Sometimes written on top of that arrow, you might see a little delta symbol, and that usually means heat. You also sometimes see catalyst written up there. So maybe it may say platinum, maybe it may say H plus for an acid catalyst. A catalyst is something that's added to a chemical reaction. It's not a reactant, it's not a product. It doesn't get used up either. It's really just there for the sole purpose of usually speeding up that chemical reaction. So sort of facilitating that reaction to occur a lot quicker. And sometimes, and a lot of times in equations, that's what ends up on the arrow up on top. Another thing sometimes you may see up on top of that arrow is you may actually just see water up on top of that arrow. And when you do see water up on top of the arrow, that usually implies that something has been taken and sort of dissolved in water. So for example, like our sodium chloride there, you may actually just see sodium chloride goes to sodium chloride. And again, here, what this is implying is that we took some solid sodium chloride and we dissolved it in water, and obviously we got a sodium chloride solution. So sometimes you'll see a lot of those sort of things written on top of the arrow, and again, that indicates some information about what's going on in that particular reaction. Now, another important relationship that we see when we look at a chemical reaction is a way that we can sort of read it, if you will. And there's a couple of different ways that you kind of look at a chemical reaction and sort of understand what all those things mean. When we do have a balanced chemical reaction like we see here, again, we use coefficients to balance those equations, which are the numbers in front. And just to know that this is balanced, you can see you have two magnesiums on the left and right. And we have two oxygens there. 2 times 1 is 2 oxygens there. So again, this is a balanced equation, and you should always have a balanced equation whenever you're using it, unless it's an odd question that says write the unbalanced equation, but usually you want the equation to be balanced. And those coefficients are really important sort of relationships that we'll see, not necessarily in these chapters here, but in the next chapter where we're going. And we could say that, for example, there are 2 atoms of magnesium react with 1 molecule of O2, forms 2 formula units of magnesium oxide. Formula units, as I think we might have touched upon, but just in case we didn't, formula units is a term that is sometimes used for ionic compounds, because technically ionic compounds are not sharing electrons and they're not molecular. And so sometimes for ionic compounds, they'll use formula unit. They'll even, instead of a molar mass, they may use formula mass, like we talked about. And it's really the same thing. It's just another way of sort of displaying it. And it's really to signify that really that's an ionic compound, no sharing of electrons. So that's what formula units basically means. But the relationship that we will see the most in this class and most of the time that you will be using is this relationship here. And we'll talk more about it, obviously, when we get to stoichiometry. But this is what is sometimes referred to as the mole-to-mole relationship. And we could use those coefficients basically to say that there are 2 moles of magnesium react with 1 mole of O2, forms 2 moles of magnesium oxide in that case. The last relationship is just a relationship that we talked about in terms of conservation of mass earlier on in the semester. And basically, because there is conservation of all the elements as you go from reactants to products. If you have 2 magnesiums on the left, you have 2 magnesiums on the right, and those magnesiums will have a certain molar mass on both sides because they're both the same element. So if you add up all the molar mass on the left-hand side there, 32 grams of O2, again, that's 16 grams each for each oxygen, plus the 48.6 gives you 80.6 on both sides. So we have that conservation of mass in terms of the elements because we do have the conservation of elements. The only sort of relationship that we don't use is the gram to gram relationship. So there is no gram to gram relationships like that. So mainly we'll do that mole-to-mole relationship. And obviously we'll talk more about that when we get into stoichiometry after we're done with this sort of chapters here. So let's talk about balancing equations, and it's really important when we do balance equations that you always have the equation balanced. So highly recommend that if you do have a chemical equation given to you, that you take a moment and make sure that it really is balanced. I would say probably if you see some numbers in it, it's probably balanced unless somebody's trying to kind of mess you up there, but in most cases it probably would be balanced, but it doesn't hurt to take a moment to check. I definitely would check if you see an equation there's no numbers in front. So as we talked about before, when we do balance an equation, it is always the numbers in front that we change, which are your coefficients. So you never, if you had, say, something like water, you never change any of the subscripts. If you change the subscripts, you're obviously changing what that is, and it will no longer be water. You also never do anything weird that people sometimes want to do, which is like just kind of insert numbers, big numbers in between things. So you never want to do that either. So only those coefficients that come in front of the formulas is what you should change. Now, when we do balance an equation, there's really 2 important things to remember when you're all said and done. When you're all said and done and you're balancing an equation, you need to have all whole numbers for those coefficients. So when it's all said and done, everybody's got to be a whole number, and it needs to be the simplest set of whole numbers. So what I mean by that, for example, is we could actually use my bad example here. So if we look at all these coefficients, and it is balanced, right? Everybody's got 2 A's on both sides, 2 B's on both sides. But when we look at all 3 of these coefficients here, 2, 2, and 2, we actually could reduce those coefficients down to 1, 1, and 1, and we would want to do that. And that would get us the properly balanced equation in this case. And that does sometimes happen because sometimes people can see sort of maybe larger numbers to use to balance the equation. But if you do see those larger numbers and there's a way to reduce down everybody and everybody will still remain a whole number, you should do that. So technically speaking, the one with all the 2's would not be the properly balanced equation because we could reduce it down to basically 1, 1, and 1. All right. So let's talk about sort of the steps here of balancing an equation. First off, you do want to write the correct formulas on the reactant side and product side. So this would be a situation where you're given everything in words. So it's really, really important if you're given everything in words to follow those rules we talked about with nomenclature and make sure that you are starting with the correct formulas to begin with. If you do not start with the correct formulas to begin with, you'll probably be there all day trying to balance the equation and it will never balance because you're not starting with the right formulas to begin with. So that's usually a very big problem for people. They try to write the formulas and they don't get the right formulas, and they can't understand why things don't balance. So if you find yourself in that situation and you wrote the formulas, take a look at your formulas. That might be an issue. The other important thing is when you're sort of writing the formulas, and sometimes you're given just the reactant part and you need to predict what's happening on the product side, it's always important to write the correct formulas regardless of the balancing. And we'll see some examples as we go through these chapters where people sort of mess up on those things. And what I mean by that is sometimes people try to write the formulas on the product side and balance at the same time. And they're like, oh, that's Na2 something on that side. I better put like Na2 on this side, even though the sodium's +1 and it doesn't need 2 of them on this side. So you want to make sure you do it as sort of in that order, correct formulas first, and then go back and balance. Don't try to do both of those things together, because that usually leads you to the wrong formula. And again, a situation where you'll be there all day trying to balance things. So for example, if we have ethane reacts with oxygen to form carbon dioxide and water, this would be the unbalanced equation here. C2H6O2 goes to CO2 and water. Also, an important thing to remember is those diatomic molecules, things like oxygen, hydrogen, nitrogen gas. Remember that sometimes they may just be called molecular oxygen, molecular hydrogen, molecular nitrogen, and that's basically them by themselves, and they come as twos. So that's also a very common mistake that people make is, again, they just go O for oxygen, not the O2, or H for hydrogen, not the H2. And again, not going to work out right because you're not starting with the correct formulas. So once we do this, sometimes it's really kind of a good idea to make a little table here. So for example, here we would have on our reactant side, our product side, and have our elements there. And in this particular case, on the left-hand side, we have 2 carbons. On the right-hand side, we have 1. On the left-hand side, we have 6 hydrogens. Right-hand side, we have 2. Left-hand side, we have 2 oxygens. Right-hand side, 2 oxygens here, plus 3 over here is, plus 1 more is 3 on the right-hand side. So sometimes this table really does give you sort of a good game plan as to where to start. We can see that nothing's balanced, but probably the easiest thing to balance in this case would be the carbon. So we could put a 2 in front of it. And when we do that, again, nothing really changes on the left-hand side. On the right-hand side, we now have 2 carbons. We still have 2 hydrogens. And now for oxygen, that is 4. And 1 more over here makes 5 in terms of oxygen. And again, this table again helps you sort of visualize maybe where to go next. You could look at it and go, okay, I fixed the carbon. I got hydrogen and oxygen. Hydrogen here seems like it would be the easiest thing to balance up front. I could do that again by putting a 3 there in front of the H2O. And when I do that, I still have 2 carbons. Hydrogen now becomes 3 times 2, which is 6. And our oxygens were now up to 4 and 3, which would be 7 in that particular case. So I highly recommend using a table such as that, and it will kind of help you focus on where you need to go. Clearly, we're not done with this one. We still have the oxygen we need to fix, so we'll take a look at that in just here in a second. But again, a reminder that only the coefficients should be what should be changed. So actually, I'll just finish it up here and then we'll roll that so I won't write over everything. So at this point, if we look at our carbon and our hydrogen, we're balanced, but we are not balanced here with our oxygen. Clearly on the right-hand side, we don't want to go back and change any of those numbers because it's going to change everything else. So we do want to focus on our oxygen over here. We basically need to make that 2 into a 7. And there is one way that you could do that. There's a couple of ways you could do that, but the easiest way you could do is use a fraction. So for example, if I use 7 over 2, let's see what that does on the left-hand side. That gives me 2 carbons, gives me still 6 hydrogens, 7/2 times 2 is 7 in this case. And at this point, you can see by using a fraction, we are balanced, right? But there is a problem with that, and that problem is what we talked about up here. When we are all said and done, we have to have all whole numbers for those coefficients. So we cannot leave it as a fraction. So this is a good demonstration that you can use a fraction to balance the equation, but you do have to get rid of the fraction. So to get rid of a fraction, you need to multiply everybody, not just the fraction, by the denominator, right? So we'll multiply everybody by 2. And if we do that, we get 2C2H6 plus 7O2 gives you 4CO2 and 6. Get a calculator here in a second. 6H2O. And if we didn't mess anything up, we should still be balanced. So if we look at the carbon, we got 4. Hydrogen, 2 times 6 is 12. Oxygen is 14. Right-hand side, we have 4 carbons. 4 times, we'll go over here, 6 times 2 is 12 hydrogens. And for our oxygen, we have 8 here, and 6 more gives us 14. So we are still balanced. This again would be the properly balanced equation here. Again, all whole numbers, simplest whole numbers, and you can use a fraction as you see here to balance it. Oftentimes will happen just like this, where you have an element in sort of its diatomic form by itself, and then that element and a couple of things on the right-hand side. That's a very common place where fractions are used. So you may say to yourself, you know, how do you choose the right fraction? It's a pretty simple sort of formula. When you're choosing a fraction, the number on top is the number you need. So if you remember, we needed a 7, right? Basically. So that's why we want 7. And the number on bottom should match that number down there. So the number on the bottom should match the subscript. So again, that's how we got to 7/2. Number we need on top, number on the bottom matches the subscript. And usually that's a pretty good way to pick the right fraction. Any questions on those steps there? Now, you don't have to use fractions in everything. It does come up a lot. If you can visualize sort of seeing the larger numbers, obviously you could use those. But it's very helpful sometimes. Okay, so let me just kind of roll through this so you can see everything in case you want to watch this back later and you need to go to sleep, help you sleep, right? There we go. So this is everything we just worked through. So I'll let it roll there so you can, at least if you want to look at it later, you can see it. And again, in terms of the table, you don't necessarily have to make a table. I probably would make a table at the end just to verify that it's balanced. I have seen a lot of exams and stuff where people think it's balanced and it's like nowhere near balanced. So just for your own sake, you may be helpful to make the table as you're doing it. But if you feel you don't need it, you don't have to make the table. But I'd probably at least at the end make a table just to verify that you did balance it right. Unless you're very confident, obviously, that you did it okay. All right, so why don't you try some here? Why don't you balance this equation? So take a minute or so here and see what you come up with. Okay, let's take a look here and see. So again, we do make that table on the reactant side, product side. We have nitrogen, oxygen, hydrogen. So on the left-hand side there, we have one nitrogen. Right-hand side, we have two. Left-hand side for oxygen, we have one. Right-hand side, we have one. And for hydrogen, two on the left and two on the right. So everything looks pretty good except for nitrogen, which obviously would be a pretty good spot to start. So again, just a coefficient change. So we're going to put the two there, going to give us two nitrogens. That now will give us two oxygens and still the two hydrogens. So usually what happens is obviously you fix one thing and kind of mess up something else. But here again, we have some pretty good direction that oxygen probably would be a pretty good place to go. So we could fix the oxygen on the right-hand side by also putting a 2 in front of the water. And when we do that, we have two nitrogens. We now have two oxygens, 2 times 1, and 2 times 2 is 4 hydrogens, which means now to finish it up, we just need to come back and put a 2 in front of the H2, and that gives us 2 nitrogens, 2 oxygens, and 4 hydrogens there, and it is balanced. Any questions on that particular one? So again, a reminder that just the coefficients, none of the numbers in between. We don't change any of the little numbers or anything like that. Okay. Why don't you try the next one then? See what you come up with. Okay, so let's take a look at this one here. Again, same idea. If we're going to make like a little table, we got carbon, hydrogen, and oxygen. Reactant side, product side. Left-hand side, we have 3 carbons. We have 8 hydrogens and 2 oxygens. Right-hand side there, we have 1 carbon, 2 hydrogens, and 2 oxygens here, plus 1 more over here gives us 3. So not much going on here in terms of balance. So probably the easiest thing to start with would be our carbon. We could fix that by, again, putting a 3 in front of it. When we do, that gives us 3 carbons. Hydrogen is still 2. And now our oxygens are up to 3 times 2 is 6, plus 1 more is 7. So we fixed our carbon. Everything else still not balanced. So to fix that, again, the hydrogen, since it's by itself, unlike oxygen, which is in a couple of things, would be the easiest thing to take next. So to fix that hydrogen, we're going to put a 4 in front of the water. It's going to give us 3 carbons. It's going to give us 8 hydrogens. And now our oxygen is 3 times 2, which is 6, plus 4 times 1, which is 4. So 6 and 4 is 10 total oxygens on the right-hand side. At this point, we now could go to the left-hand side and see that the oxygen can be fixed by putting a 5 in front of it, giving us 3 carbons, 8 hydrogens, and 5 times 2 is 10 oxygens. Any questions on that particular one? All right, then let us continue on then. Got a couple more, I think. So why don't you do this one here? I'll give you the formula just in case. Okay, so let's take a look. We got here, reactant side, product side, and we got boron, oxygen, and hydrogen. So we got 2 B's on the left and 1 on the right. 3 oxygens there, plus 1 more gives us 4. Now, in terms of oxygen on the right, we do need to distribute this 3 in. So that's 3 times 1, which would give us 3. On the left-hand side, we have 2 hydrogens. Right-hand side, same deal. We got to distribute that 3 in. So 3 times 1 would give us 3. So not much balance here. We don't have a lot to work with, so might as well start with the boron. So we have 2 on the left and 1 on the right. So we could fix that by putting a 2 in front of it. When we do, on the right-hand side, that gives us 2 borons. Now for the oxygen, we had 3, but we also then need to distribute that 2. So that's basically 3 times 1, which is 3. And then 3 times 2 is 6. And same thing with the hydrogen. 3 times 1 is 3, and 3 times 2 is 6. So we fixed the boron, the oxygen, hydrogen, not correct. Obviously, we don't want to change that number in front on the right-hand side because that will change everything else. So let's try to fix what might be easiest here, and that would be the hydrogen. I got 2 on the left, 6 on the right, which means I could put a 3 in front of the hydrogen. When I do that, I got 2 borons. Oxygens, I have 3 here, and by putting that 3 there, it actually fixed the oxygen as well. It gives me 3 more, and that gives me the 6. And 3 times 2 is 6. So this sometimes happens that, you put a number down and it fixes the one you're going for, but it may also help one that you were not necessarily trying to fix at that point. Any questions on that particular one? Okay, let's take a look at one more, I think. All right, let's take a couple of minutes here and see what you come up with on this particular one. Okay, so let's take a look and see how we're doing. So we have nitrogen, hydrogen, and oxygen here. So left-hand side there, we have 1 nitrogen. Right-hand side, we have 1. Left-hand side, we have 3 hydrogens. Right-hand side, we have 2. And left-hand side, 2 oxygens. And we have an oxygen in each of these guys, which makes 2. So it does appear almost like it's pretty balanced there. Just the hydrogen is not balanced. So on the left-hand side, we have 3. Right-hand side, we have 2. So sort of our common number there between those is 6. So to get our hydrogen on the left to 6, we need a 2. Get our hydrogen to 6 on the right, we need a 3. That's then going to give us 2 nitrogens on the left. Hydrogens, we will have 6. And oxygens, we will have 2. Right-hand side, we still have 1 nitrogen. Hydrogen, we have 6. And oxygens, we have 3 here and 4. 3 here and 1 more makes 4. So the next easiest thing probably to take care of would be the nitrogen. So we could fix that by putting a 2 on the right-hand side. And that will give us 2 nitrogens, still the 6 hydrogens. Our oxygens are now up to 2 on the here, and 3 more makes 5. So at this point, we've now balanced everything except for our oxygen. We only have really 1 spot to fix it, which is here. And we're in that situation where we basically need to turn that 2 into a 5. So we do want to use a fraction here to do that. It's probably the easiest way. Again, remember the fraction is on top, the number we're looking for. So we're looking for a 5. So we need a 5 on top. And the bottom number should match this one, which would be 2. So we would want to go with 5 over 2. And when we do that, again, gives us 2 nitrogens, 6 hydrogens, 5/2 times 2. 2's cancel, right? Gives us 5. Gives us 5. As we talked about, although we are balanced technically at this point, this is not the correct way to do it because we still have a fraction. So everybody needs to be whole numbers here. So in this case, we need to multiply everything by the denominator, which is 2. And if we do that, that will give us 4NH3 plus 5O2 gives us 4NO plus 6H2O. And again, if we didn't mess anything up along the way, this should still be balanced. So we have on the left 4 nitrogens, we have 12 hydrogens, and 5 times 2 is 10 oxygens. Right hand side, we have 4 nitrogens. 6 times 2 is 12 hydrogens. We have 4 oxygens here and 6 more in that last one is 10. So we are balanced in this case. Any questions on balancing there using a fraction, anything like that? So obviously you do need to know how to balance equations, but let's give you one more to try just to see how you do. Why don't you do this one here? All right, so I want to take a minute or so here and come up with the balanced equation. Okay, so sometimes when you see an equation like this, you definitely could follow the same sort of approach that we did before where you sort of take it element by element, which is perfectly fine. But sometimes it's a lot easier, especially if you look at it and you see those polyatomic ions that are in there. So for example, here we have SO4. On this side, we have SO4, which is sulfate. We also have phosphate on each side. And if you have those polyatomic ions that are basically the same on each side, sometimes it's easier just to balance those as sort of whole units instead of sort of going element by element. So for example, if I were to do this equation here, I would look on the left-hand side and see, okay, I have 3 of those sulfates. On the right-hand side, I only have 1 sulfate. So I can balance that quickly by putting a 3 in front. That gives me the 3 sulfates, which is what I need. But it did just change my sodium from 2 to 6. So that would be the next place I would want to go. and fix my sodium by putting a 2 there, giving me 6 sodiums, but obviously phosphates attached there. So that also gives me 2 of those phosphate units, which then I would come over here and go, I only have 1. So to fix that, I could put a 2 in front of it, which gives me 2 phosphates, also gives me 2 iron. And as you can see, that's okay because I need 2 iron as well. So sometimes it's a lot easier, especially if you have those polyatomic ions involved. They look the same on both sides, to kind of keep those guys together and balance them as kind of units, if you will. And just like we just saw here, at some point, usually everything will sort of fall into place, and you know, you could usually balance it a little bit quicker. So you could go individual element by element. There is probably a little bit more room for error in that case because you have a lot of multiplying in, and then when you put coefficients, multiplying across and trying to keep track of kind of those individual guys. Again, it's sometimes a lot easier to kind of just keep them together and balance them that way. Any questions on that there? Questions on balancing equations in general? All right, then we will continue on. A reminder, if you do have questions, feel free to ask them there in the chat box. So let's talk a little bit about electrolytes. So electrolytes are basically substances that when they dissolve in water, they basically can conduct electricity. And as we'll see, there's really 3 types of electrolytes. There's strong electrolytes, there's weak electrolytes, and there's really non-electrolytes like what we got there on the bottom. And when you have something that's, say, a strong electrolyte, as we will see, it 100% breaks into ions. So if you had some sodium chloride solution, in solution, you basically have sodium ions and chloride ions. You have 100% the sodium ions floating around and the chloride ions floating around in a solution of sodium chloride. You have no sodium and chlorine units still together at that point. They've completely broke apart. And really what makes it a good conductor of electricity is that idea that you produce a lot of ions. So the ions kind of help complete the circuit, if you will, and conduct electricity really well. So a strong electrolyte, for example, because it 100% breaks apart into ions, produces a lot of ions in that solution and will conduct electricity really well. As we'll see in a second, that's like a light bulb that goes off very, very brightly. So you could take a light bulb, connect a couple electrodes to it, and put it in a strong electrolyte solution. Light bulb will shine very, very brightly. Now, a weak electrolyte, as we will see, also breaks apart into ions. But it mainly stays together. So for example, if you take HF, which is a weak acid, it will break apart into H plus and F minus. But unlike a strong electrolyte, you produce only a few of these ions in solution. It mainly stays together. So because it mainly stays together, it's basically a weak electrolyte, and it's still considered an electrolyte because even though it does mainly stay together, it's still able to produce a little bit of these free ions. And because it's able to produce some free ions, it's able to conduct electricity still. It will not be able to conduct electricity anywhere near a strong electrolyte. So in terms of the light bulb example, which I think we have some pictures coming up here in just a second, but in terms of the light bulb example, the light bulb will come on, but it'll be very dim. So it's still able to conduct electricity, but again, nowhere near the effect that a strong electrolyte can, because again, it doesn't have as many ions. The other kind of key thing that you typically see with a weak electrolyte are the arrows. And these arrows are heading in both directions. And when it does, there's a forward direction which goes from reactants to products, and there is a reverse direction that goes from products to reactants. So in a reversible reaction, for example, that H plus and F minus, some of them will come back together and form the HF again. So it's kind of like a two-way street. When you have a weak electrolyte, it'll go one way. Some of that stuff will come back the other way. As you'll learn if you do go to the next class, when the rates of those things equal each other, the forward reaction and the reverse reaction, that's what's known as reaching chemical equilibrium at that point. And that's different than a strong electrolyte. A strong electrolyte pretty much is a one-way arrow. As you can see here, it's a one-way street. Everybody essentially here is dumping out on the product side into those ions. Nobody's coming back the other way. And again, that's a major difference between sort of a strong electrolyte and a weak electrolyte. Again, they both are able to produce ions, but a weak, very little ions mainly stays together. A strong 100% ions, nothing staying together. And lastly, our non-electrolyte here does dissolve typically, but does not produce any ions. So because it dissolves, so for example, if you take something like sugar, we know if you put sugar in water, it will dissolve. But sugar is made up of carbons, hydrogens, and oxygens, and those are all nonmetals, which means they're going to be held together by sharing of electrons, covalently bonded. So when they go for a swim, they are going to dissolve, but they will still stay together and produce no ions. So since it produces no ions, a non-electrolyte will not conduct any electricity, so the light bulb would not go on. So sort of that example here, that would be what a non-electrolyte would look like. That's a light bulb hooked up to some electrodes. It's in a non-electrolyte solution here, and you can see light bulb does not go on. If we put it in a weak electrolyte solution like our HF here, you can see the light bulb comes on and it's kind of dim, but it's still able to come on, again, because in that situation, still able to produce a little bit of ions, but mainly stays together. But because it still is able to produce that little bit of ions, still able to conduct electricity. And lastly, there's our strong electrolyte there, like a sodium chloride solution. You can see conducting electricity really, really well. Light bulb goes off very brightly, again, because pretty much the only thing you got in this solution is nothing but positive and negative ions floating around, which again, like I said, sort of helps complete the circuit, if you will, and allow the light bulb to go on very, very well and conduct electricity very, very well. So here's a little bit closer look at what we were just talking about here. Again, a strong electrolyte 100% dissociates. That's a fancy word of saying 100% breaks apart into ions. And as I was mentioning before, in the solution, 100%, this is what you have floating around. You have none of the sodium chloride ions still together, or compounds still together. Now, a secondary question is, if you just took, say, the solid, just the solid sodium chloride, would it conduct electricity? So if you took that same sort of light bulb and you stuck it into just the solid sodium chloride, it actually would not conduct electricity. It's not until you dissolve it that you free up those ions, the positive and negative ions floating around, that it will conduct electricity. So just a little note on that. This is acetic acid, which is essentially vinegar. And acetic acid is also a weak acid. And again, you can see with the arrows here, that reversible arrows heading in both directions. So this is a weak electrolyte because in solution, you will produce a few of these guys. But if you really want to know mainly what you would have in solution, you would still have this guy all still together, is mainly what you would have in that particular solution. And again, that's different than over here where 100% of what we got going on would be ions. And again, that reversible arrow indicates that the reaction occurs in both directions. So again, heading from our reactants to our products is the forward direction. Heading backwards from products to reactants is the reverse direction. And when somebody says it reaches equilibrium or chemical equilibrium, this is really what they're talking about is the rate. Not that you have the same amount on each side, but it's the rate of the forward reaction will equal the rate of the reverse reaction. So essentially, just as quick as it goes to the product side, it's just as quick coming back the other way. And as you'll learn in the next class, basically what that means is everybody locks into place at that point in terms of where they're at, because as soon as you go this way, it comes back the other way. So there's not a lot of change that occurs in terms of concentrations when something reaches chemical equilibrium, unless you do something to mess it up. So hydration is the process where basically ions sort of get surrounded by water. And so, for example, when we do talk about something like sodium chloride, when it does break apart into water, in water, we get aqueous sodium ions and aqueous chloride ions. So really, what does the aqueous really sort of symbolize here? When we use that symbol, it's really this situation. The aqueous basically means that there's water that surrounds each of those ions. So water, as we talked about, is a polar molecule where the oxygen part is more negative and the hydrogen part's more positive. So when like a sodium ion is positively charged, like the guy here, goes into solution, what essentially happens is it gets surrounded by water. And it's the oxygen side of water, which is negative, surrounds it, right? Opposites attract. So the positive and negative attract each other. And it surrounds all the positive ions. Our chloride, for example, our negative ion, also gets surrounded by water, but it actually gets surrounded by the hydrogen side of water, which is more positive. So the positive side of water will surround the negative ion. And it really does two things. This is really what happens when something dissolves. Although we think about it, it's like disappeared, it's gone, it went away. It really didn't go away. It really just got mixed into sort of the water network. And when it does that, you no longer can sort of visually see it because there's so many water molecules around each of those ions that it sort of disappears, even though it really doesn't disappear and it's still there. And if you've ever done an experiment where you take something that's like salt water and you heat it up and you evaporate off the water, right? So if we took a solution of sodium chloride and we heated it, once we start heating it, all these water molecules, right, that are surrounding these ions are going to start to evaporate. And what's going to happen is eventually when they all kind of evaporate away, you're left with your positive ion, you're left with your negative ion, and now you have none of those waters in the way. And these guys have a super high attraction for each other, the cation and the anion, and they will come back together and you will see that solid come back. So if you ever done an experiment where you sort of evaporate off the water and you're left with sort of a solid residue, that's sort of what's happening here. The water acts to do two things. It helps it dissolve, but it also prevents the positive ion and that negative ion from coming back together in a solution that it's in because they have a very high attraction. So when we evaporate off the water, there's really nothing to prevent those really strong attraction from coming back together, and they basically will come back together. And visually what we see at that point would be like a solid has sort of reappeared, if you will. So this would be like an experiment that maybe you've done before. You have sort of a solution or you dissolve a solid, it sort of disappears, you evaporate off the water, it comes back. And again, that's because we got rid of the water. And a non-electrolyte, as we talked about, again, is something like sugar where it will dissolve, but because it's covalently and electrons being shared, there's no ions being produced and obviously would not conduct electricity. So this is a table, not from your book, but I think you probably have a similar one. A lot of these guys are strong acids and strong bases. Strong acids and strong bases are strong electrolytes. They 100% break apart into ions. Any type of ionic compound typically is a strong electrolyte because when it goes into water, it's very, very soluble because of what we just saw in the previous slide. There's some weak electrolytes, and a lot of those are weak acids and weak bases. So acetic acid, hydrofluoric acid, nitrous acid, ammonia, those are all weak acids and bases. On the right-hand side there is some non-electrolytes. And you can see most of those are all carbons, hydrogens, some nitrogens, so all non-metals together, covalently bonded, no ions being produced. All right, any questions on electrolytes? So let's talk then about a particular type of reaction, which is a precipitation reaction. And this is really under a big class of reactions, which are known as double displacement reactions. So sort of under this kind of big umbrella of double displacement reactions, a precipitation reaction is a certain type of it. And a double displacement reaction has this general formula: AB plus CD. A and B are an ionic compound. C and D are also an ionic compound, which means there's a positive guy and a negative guy together, and a positive negative guy together on the other guy. And what ends up happening is the two positive guys basically will switch partners and make two new ionic compounds on the other side. So A and D would come together, and C and B would come together here. And we basically get this double switch between the two cations, and they make these new products. And if one of these products makes a solid, which again is sometimes referred to as a precipitate, which is abbreviated that PPT, that is what is known as a precipitation reaction. So precipitation occurs a lot of times when you take two solutions, no solids involved, mix them together, and basically because those two solutions have a bunch of ions floating around, they both have basically in this test tube, positive and negative guys floating around. Say in this test tube, something else, positive and negative guys floating around. When you mix them together, there is possible a certain combination of a positive and negative guy when they come together will make a precipitate, which is, you can see here, this yellow precipitate, which is lead to iodide, is formed. And again, that's a result of mixing two solutions that don't have precipitates together, but when a certain number of ions get together, or certain types of ions get together, they can form this sort of solid that occurs. Now, precipitate does not necessarily mean that it's going to be like a rock hard solid or anything like that, but it could become cloudy, could be some floating sort of particles that occurs, or it could make something that really rock hard that drops to the bottom. So if we look at this reaction here, this is lead to nitrate. Lead is a positive guy, nitrate's a negative guy. This is sodium iodide, positive and negative. And again, what's going to happen here is these guys are going to switch partners. So when you think about what's on this side, you want to think about these guys in their basic units. So the basic unit of this guy is lead with a +2 charge. The basic unit of NO3 is nitrate. And you can see at this point, even though it has a 2, I don't really care about it at this point. Over here, the basic unit of this guy is a sodium with a +1 charge and an iodide with a -1 charge. So this is where people sometimes go really bad, is they see this 2 here and go, okay, I need to incorporate it somewhere as I put them together. But when you want to, if you weren't given these formulas on this side, what you want to do is just take the basic units of what make these guys up and then put them together correctly like we did with nomenclature, which means this positive guy will come over here. And that is a +2 and a -1, which means we do get PbI2, the correct formula on this side. We need 2 of the iodides. Also means when we take the sodium is going to come over here to the nitrate. The sodium is +1, the nitrate is -1, which is how we get to this formula. I can't tell you how many people will do this move like, something maybe like this, because I see all these 2s, so I need to make sure I keep those 2s, and this is not the right formula at all. So you want to make sure that, again, as I was talking about earlier, you get the right formula first, and now you can see it's not balanced. Then you could go back like they did here and put those coefficients in front to balance it. So that's what I was talking about earlier, that sometimes people try to write the formulas and balance at the same time, and you end up getting the wrong formula. And usually what will happen is you'll be there all day trying to balance it because it will never balance correctly. So always want to get the right formula, which is just the basic parts of each of these things, regardless of extra twos in the fronts, threes in the fronts, whatever it may be. Just the basic units and put them together correctly. Any questions on that? Now, this is the precipitate, I'll say that right, precipitate here. When the lead-2 ions come together with the iodide, it makes this solid. Now, the way it's written here, before I scribbled all over it, is what is known as the molecular equation. Now, what's really happening in this solution is when these guys go in, because these are aqueous, they're actually going to break apart. So we could write another equation which really describes what's happening when we mix these together. And this lead-2 nitrate, which is aqueous, is a strong electrolyte, which means in solution you would have lead with a +2 charge as aqueous. This would make nitrate. But when we look at the nitrate, there is not one of them, but there's two of them. So that two will actually come to the front. Then the sodium iodide would also break apart into ions. So you would get 2 sodium ions. This 2 would also go for the iodide, and you would get 2 iodides. Now on the other side, we have this lead-2 iodide, which is this yellow solid. And as you can see, this yellow solid is not going to break apart. So when you write this type of equation, which you're writing right now, anything that's a solid, anything that's a pure liquid, and anything that's a weak electrolyte will actually stay together. So here we would keep that PbI2 together because it's a solid. But this guy is aqueous and would break apart. And I'll just write it down here since I ran out of room. We would get 2 sodiums and 2 nitrates as well. This equation that I just wrote here is sometimes referred to as the total ionic equation, our complete ionic equation. And it basically describes what's happening in this reaction when it's in solution. So basically in a total ionic equation, you break apart everything except anything that has a liquid, a solid, or is a weak electrolyte. Now, when you look at this equation, which I'm going to rewrite really quickly here, hopefully much neater. And I've got the 2 there. There we go. 2 iodides. Let's do it that way. I don't know if that's much neater. So when we look at this equation, we will be able to find ions that are on both sides that look exactly the same. And we do have a nitrate that looks exactly the same as our nitrate over here. We also have a sodium that looks exactly like our sodium over here. And these ions that are found on both sides are what are referred to as spectator ions. So these are spectator ions, these 2 guys, and on this side as well. And spectator ions, much like it sounds like, are just there to observe, right? If you're a spectator, you're just watching. And that's basically what happens with these ions. They're not really participating in the actual reaction that's taking place. And what we do with spectator ions is we cancel them out. And what we're left with is a third type of equation, which in this case would be Pb2 plus my 2 iodides. Thank you, I found the 2 there. I got lost along the way. And that forms our PbI2 solid. And this equation here really describes what happens when we mix those two solutions together. What's really happening is the lead 2 from the lead 2 nitrate is coming together with the iodide to form lead 2 iodide. And this is what is known as a net ionic equation. So when we deal with sort of precipitation reactions or double displacement reactions, there's kind of three types of reactions or equations that we could write. One is a molecular equation, where we pretty much write everything with their correct formulas and make sure it's balanced. The next one is our total ionic equation, which I wrote really crappily here twice, right here. And that is the equation where we break apart anything that can be broken apart. And those are things that are basically strong electrolytes. And usually that means that anything that, again, that's a pure liquid has the L symbol next to it, you wouldn't break it apart. Anything that's a solid, you wouldn't break it apart. Actually, anything that's a gas as well wouldn't break apart usually. And anything that's a weak electrolyte, you wouldn't break apart. And then once you write that total ionic equation, you should be able to look on the left-hand side of the arrow and the right-hand side of the arrow and find ions that look exactly the same and actually have the exact same numbers of ions on each side. So these both are 2 and these are 2s, right, on each side. And they should completely cancel out. And what you're left with is our net ionic equation, which adequately sort of describes what's truly happening in that particular reaction. Any questions on that there? Okay. Much prettier picture, I guess, what I wrote about. So when we do write these sort of net ionic equations, what we want to do is make sure that we have the balanced equation. We want to write the ionic equation showing the strong electrolytes that have completely broken apart. We want to cancel out any spectator ions, and we want to make sure that everything's balanced in terms of atoms and the charge. So why don't you take a moment here and write the net ionic equation for silver nitrate reacting with sodium chloride and see what you come up with. Okay, so let's take a look. So again, you just start giving things in words. You just want to start with the right formulas. So silver nitrate is AgNO3, silver being +1, nitrate being -1. And sodium chloride is NaCl. If you weren't sure what type of reaction this would be, again, you can see that this is a positive guy, negative guy, positive guy, negative guy. That's your classic double displacement reaction. And when we want to go to the other side, again, really the silver nitrate is silver with a +1 charge, nitrate with a -1 charge. Sodium chloride is sodium with a +1 charge, and chloride with a -1 charge. So the first thing that would come together is our silver. We'll switch partners and come up with our chloride. So when we put those together as -1 and +1, just like we talked with nomenclature, we would get silver chloride, which is a solid. The other thing that will happen is our sodium ion, which is +1, will come together with our nitrate ion, which is -1. And again, we just need one of each of those. And this would give us our equation here. We want to make sure that it's balanced. So I have one silver on the left, one on the right, one nitrate on the left, one nitrate on the right, one sodium on the left, one on the right, and one Cl on the right. This is our molecular equation, balanced. We now can write a total ionic equation by breaking apart our strong electrolytes, which is basically our ionic compounds. So our silver will again break apart into a silver ion plus a nitrate ion. Our sodium chloride would break apart into a sodium ion and a chloride ion. Our silver chloride, which is a solid, will stay together and not break apart. And our sodium nitrate would break apart into a sodium ion that's aqueous, which is what that little scribble is there, and a nitrate ion, which is aqueous as well. We're actually going to see that in the next slide, I think, how we could determine which one will be a solid in just a second. But the quick answer is there's solubility rules, which we'll see, I think, coming up in the next slide. And that will help you determine what will be a solid and what will not. So we'll take a look at that in just a second. Yeah. All right, so when we look at this, this again is our total ionic equation. And again, we broke apart everything into ions that could go into ions. Anything that's a solid, a liquid, a gas, or a weak electrolyte kept together. When we look on both sides, we do see the nitrate on the left matches the nitrate on the right. The sodium on the left is exactly what we see here on the right in their ion form. And these guys, again, would be our spectator ions, right? So we do cancel them out. And as you can see, they do completely cancel out. And what we're left with is a silver ion plus a chloride ion coming together to make our silver chloride. And basically, this is our net ionic equation. Basically telling us that when we mix our silver nitrate with our sodium chloride, it is the silver ion from the silver nitrate that comes together with the chloride ion from the sodium chloride that makes this insoluble solid or precipitate. Question on how to write those three different types of reactions. Okay, so let's get to your questions, which I think is coming up with is how do you know, like, if I mix these two things, would I expect a solid? Would I not expect a solid? So I'm hoping I'm correct that that is what's coming up. And it is. Okay, good. So it is solubility rules, and really these solubility rules is what helps us determine whether or not when we mix a couple of things, for example, would we expect to see a solid. So solubility in general is the maximum amount of solute that you could dissolve in a given amount of solvent. And that's basically what makes up a solution. A solution, which is like that aqueous symbol we keep using, basically is made up of a solute, which is the smaller part, and a solvent, which is the larger part. So for example, if we were making that sodium chloride solution, The sodium chloride, which would be a solid, would be your solute. The solvent would be water in this case. Yeah, so in the case of that example, the solute would be sodium chloride and water would be the solvent. When you put them together, you basically get a solution that's being made. So there are rules which are known as solubility rules. So let's take a look at these. So these are general solubility rules of things in water. And these are things that are typically soluble, which means if they are soluble, the symbol that they typically will get is that AQ symbol. That aqueous symbol is typically your symbol that you'll get. If something is thought to be insoluble, those are the guys that get the solid symbol next to them. So if you find something that's soluble, the aqueous symbol, something that's insoluble, the solid symbol. So what we see here on this table are things that are generally soluble. So these are things that generally should get the aqueous symbol next to it. Would not expect a solid to form. Anything that contains lithium, sodium, potassium, really group 1 on the periodic table, and ammonium are soluble in everything. So there's no exceptions. So as soon as you see one of those guys in a chemical formula, you automatically know it is soluble and should have the aqueous symbol next to it. Things that contain nitrate and acetate are also soluble in everything. So those things as well, as soon as you see those things in a formula, you know it's going to be soluble and you should put the aqueous symbol next to it. Things that are chloride, bromide, iodine are soluble in everything, but there are 3 exceptions. So if you see chloride, bromide, or iodine in a formula, you know it's going to be soluble and they'll get an aqueous symbol. The exception, though, is if you see chloride, bromide, and iodine that's hooked up with silver, this is mercury 1, or lead 2, then it's actually going to be the opposite. So it would not be soluble, it would be insoluble. So these guys would get a solid symbol. These guys would get an aqueous symbol if it's not combined with anybody there. Sulfates are also soluble in everything except for these guys. So we have some exceptions here. So if sulfates with any of these guys in a formula, they should get a solid. If they are not, they should get a aqueous symbol. Now, there are some things that are typically insoluble. So let's take a look at those here while we sort of finish up this little topic here. If you see something with hydroxide in it, it is typically insoluble, which means typically it should have a solid symbol. Except though, if it's with group 1 on the periodic table or ammonium, then it will be aqueous. So again, the exception is basically the opposite. There are some calcium, strontium, and barium which are slightly soluble. Slightly soluble, most people, sometimes people will use SS for that. But most people will sort of consider slightly soluble to be more insoluble. So it's not very soluble. So it kind of leans towards the insoluble side and solid. If you have something with sulfide in it, should be solid. Except again, our normal exception, like we saw on the previous page, group 1 and ammonium, and also here barium, strontium, and calcium are group 2 guys. Carbonates and phosphates are typically insoluble, except for our group 1 and our ammonium as well. So they kind of go together, these rules, but these are things that typically get a solid. So if we go back to our original equation here, just to finish up on this, and then we're just a little bit over here, just to finish with on this idea of what we were talking about here. All right, so if we just write these formulas and we want to know, are these going to be solids, or are they not going to be solids? Again, we could use our solubility rules to help us decide. So if we just look first at the silver nitrate, although we may not be able to find silver on the periodic table on these solubility rules, we can find nitrate, which is right here. And when we see nitrate, it is soluble in everything. There's absolutely no exceptions to it, which means as soon as I see that nitrate in this formula, even though if I can't technically find silver, I do know that it's soluble in everything and it should get that aqueous symbol. Now, when I go to sodium chloride, I see sodium, and sodium is part of group 1, which I automatically see is soluble in everything. There's no exceptions, which means I know that's going to be soluble and get aqueous. I could even look at the second one if I want, which is chloride, and that also is soluble in everything except for silver, mercury, and lead, which in this case is not what's happening here. So both of those things tell us the same thing, that this guy should be soluble. And truthfully, you can stop once you get to the sodium part. Now, coming over here to my silver chloride, again, I may not be able to find silver, but if I look at my solubility rules, I do find chloride. And chloride is soluble in everything, except if it's hooked up with silver, mercury, or lead, which in this particular case, it is hooked up with silver, which means it normally is soluble, but this is an exception. So I know that now it's going to become insoluble. And that is how I know in this case that the silver chloride is going to be the solid that's going to be produced. Looking at our last guy here, sodium and nitrate, we could actually see both of those. If I look at sodium, I see it's soluble in everything. There's no exceptions, which means I could really stop at that point. But if you weren't convinced, you could still go to nitrate, which also is soluble in everything. And again, both of those things tell you that it should be aqueous. So you can see here, you could use these solubility rules to determine basically, what's going to produce a solid, what might not produce a solid. Questions on that, or how to use those solubility rules in that application. And obviously at this point, once you figure out the solid, you could go through your total ionic equation, your net ionic equation, and you could kind of figure out everything that you need. Any questions on that? Okay, so we went a little bit long there, so we'll go about 9:50 or so for lab, and I think maybe we got a study assignment on this stuff, so that'll be good. All right, make sure you type here, and then see everybody in about 20 minutes in the lab.